Alex works at Malvern Panalytical, which used to be Malvern Instruments. It's a materials characterisation company based in Malvern, one of our bigger employers here in the town. Always very supportive of the festival. Usually they have a stand at the Malvern Festival Innovation for the school students to have a look around and do some experiments. So this year they very kindly agreed also to go inside their facility and show us some of the things that they do and some of the instruments that they actually design and use for testing. So Alex, thank you ever so much for joining us and also for jumping in a little earlier in the schedule. Great to see you.
Yeah, I'm here in the Malvern Panalytical office, which is based on the Enigma Business Park in Malvern. And obviously, with sort of COVID and everything happening at the moment, we are quite an empty building. But normally, this is home to about 300 people working in this office. About 120 of those work in our research and development section. But we also produce instruments here, so if I can put my camera around. There's some office over there where R&D are normally based, and then downstairs you can see lots of racking, and that's where our instruments are built. And we build instruments here which are shipped all over the world. And as was mentioned in the introduction, these instruments are used by scientists to characterize materials. So I'll just take you into one of our labs. So this is called the Mega Lab. So we have a range of different instruments where different scientists and engineers can bring them in here to test and how they're going to perform. When we mention material characterization, what do we mean by that? So generally, a lot of our products here are used for testing powders and particles. So if I had a material which was a powder and I wanted to know the size of all of those parts, I could bring it along to one of these instruments. This is our most common instrument. It's called the mastifizer. And this uses a technique called laser diffraction, which is where we take a laser beam, shine it through the particles, and each of those particles will scatter the light at different angles, and then a range of detectors within here can see how those particles have scattered the light, and from those measurements figure out the size of the particles in the mixture. Another key parameter is shape of particles. So if I ask you to measure small things, you can imagine using a microscope. And this is another one of our products, which is an automated microscope. So if I had a powder, which is maybe used to make a drug, so tablets, so you know, like paracetamol, it's made by squashing together tiny particles. If my tablet isn't sticking together very well, it might well be because of the shape of the material. If we can disperse that under here, and then the system will move that around under our microscope, and we can take an accurate image of every single particle. We can work out the size and their shape, and then from that figure out what we need to do in our process to make our drugs better, or if we're making a new drug, how to make it the same as what we've already made before. An additional feature of this system is it can also use a technique called Raman spectroscopy, which is where we blast every one of those particles with a laser beam, and we figure out by looking at the scattering that comes from the particles, what specific chemicals make up that particle. So we can very quickly and automatedly get a lot of information about our drug sample, both in terms of the size, the shape, and the chemical composition of the material. Okay. If we wanted to measure things even smaller though, we'll get to a point where a microscope can't actually see them. So that's where laser diffraction, as I mentioned before, so that's what the mastifizer does. And here's some engineers talking about one at the moment. That can measure particles down to sort of micron level. So a human hair, we tend to talk about being of order of tens of microns thick. So that instrument can measure particles of around that size. If we want to go even smaller, and we want to measure the size of maybe an individual protein, we can't see that, we can't image that. So you might wonder, well, how do we figure that out? This is where we come to one of our other sort of main instruments, and this is a Rosetta sizer. And this is actually the product that I'm the senior scientist responsible for the development of. And this instrument can measure particles down to less than a nanometer in size. So a nanometer sounds like quite an abstract number to try and think about. So that's 0.9 zeros and then a 1 meters, that's a nanometer. And that sounds really small, but again, it's hard to imagine how small that is. So one way to think about it, if I took one of those 1 nanometer particles and put it next to a tennis ball, hopefully you can all imagine how big a tennis ball is. If I were to grow both of those things, so the particle and the tennis ball, and I keep stretching them and growing them until that 1 nanometer particle is now the same size as the tennis ball, that tennis ball will now be bigger than the Earth. So hopefully that gives you a sense of scale of how small these particles are that we can detect. The way we figure out the size of them, because we can't actually see them, what we do is, inside the system, as you can see here, underneath here, so I've taken the cover off, there's a laser and then lots of mirrors, and then our sample will be floating in a liquid in a sample holder like this. And the particles that are dispersed in there are moving around randomly, which is something called Brownian motion. And this is something that Einstein actually observed, and some of the equations we used to work out the size of these particles use one of Einstein's equations. And basically, as the particles move around and they diffuse randomly, they will scatter the light that we shine on them differently depending on how fast they move. So we can take our laser beam, shine it onto the sample, very accurately measure how the light comes back from the sample. We can then work out how fast they're moving, and if we know how fast they're moving, we can figure out how big they are. And that works all the way, like I say, down to less than 1 nanometer in size. So this technology isn't necessarily new. So the Zeta Sizer was the product name of this instrument. The first Zeta Sizer Malvern instruments made was back in, I believe, 1983, which to many of you seem like a ridiculously long time ago. And the technology worked back then, worked very well, and has been used to measure very small particles ever since. But here at Malvern, where we are sort of the world leader in this technology, we are constantly looking at how we can improve both the optics. So hopefully we can see in here there are lots of different optics. So we've got mirrors and lenses and sensors arranged in different ways to optimally put light onto the sample and how to detect it. But then also a lot of work on how we interact with the instrument and make it easier for a customer to use. So how do we take that data from what the laser is telling us about the sample and turn that into a size measurement that we can actually make some sense of? And also in this latest product, we included some machine learning. So artificial intelligence is one of the new sort of buzzword technologies which seems to come up everywhere. And the data that comes out of this instrument is very complicated. And historically, people using these instruments were generally inexpert in the technology. But over time, there aren't as many experts using these, and the instruments are being used far more widely for quality control in all sorts of different applications. So it might be being used by someone who isn't an expert, but by using artificial intelligence and a machine learning sort of neural network, we can take that data which comes off of every measurement, pass it through our machine learning algorithm, and figure out whether that data is good, or if there are any issues that maybe we need to go and change how we've prepared the sample or change how we've done the measurement and let the user know how to measure it again. So a huge area of our sort of research and development at the moment is in software and also data analytics. So as well as having the office here in Malvern, we've recently opened a centre in Bristol, where we have some close ties with Bristol University as well, where we have a team of, or an ever-growing team of software engineers and data scientists working there. At that point, I've lost track of where I'm up to with time, and I'm wondering if there's any sort of Q&A.
Yeah, exactly. No, fantastic. You're spot on time. So thank you ever so much, Alex, for giving us the behind the scenes look in Malvern Panalytical. I think it's really interesting for people to see what it's like in an industrial setting. You've got your research labs, you've got your administration, and it's quite a big building that you've got there in the business park in Malvern. So it's really nice to see on the inside. Yeah, I don't know whether there's any questions. I've been monitoring. I haven't seen any specifically come in, but from my side, I know that, traditionally Malvern Instruments, Malvern Panalytical were making the machinery, and it's very engineering, whereas now there's a lot more software. You alluded to it with the artificial intelligence and so on.
Yeah.
So actually, people that are thinking about maybe a career in Malvern Panalytical or a similar type of company, it's not all about just the engineering, is it? There's a lot of other skills that are needed for developing a product like this.
Yeah, so definitely. So we attract from a wide range of sort of STEM fields. So we have physicists, chemists, engineers. Everything that I sort of showed on the inside of the instrument has been designed by someone here. But then, as I said, there's a huge amount of work that goes on how to get from what the hardware tells us to the final answer that our customer or the user of the instrument wants to know. So I think it's something like we have 80 software engineers here at the moment, and I mentioned that 120 R&D based in this building. So you can see we have quite a huge sort of an ever-growing number of software engineers in the business. So that's definitely an area where sort of we're growing, and people who historically haven't come from, I guess, a software or data science background some of them are looking at transferring skills as well, sort of to pick up on those applications as well.
Excellent. And also you run a graduate scheme, don't you, as well, and a work experience scheme for students during the summer? Yeah,
we do, yeah. So we take, we have placements for students to join us during the summer. We've also have a year in industry program. So every year we take a number of students who are partway through their degree, who come to join us for approximately a year. And then we've had quite a few of them who've come to work for us sort of full-time after they finish their degree. And we also have a apprenticeship scheme. So we've had a couple of different apprenticeship programs where we have potential software engineers come from sort of college age, learning how to be a software engineer, moving around different teams, and then eventually sort of becoming a sort of a full-time, fully fledged software engineer. But then similarly, we've done the same for mechanical engineers and different disciplines as well.
Yeah, fantastic. Yes, the apprenticeship schemes are growing in popularity now, so they're definitely something that students should look into as well. We've had a question from Dr. Alan Smith. So he's saying that light scattering from particles is very theoretical. So do you have theorists or theoretical physicists, chemists at Malvern Panalytical as well?
Yes, we do. So, a caveat with a lot of our technologies is there is a theory applied in the analysis that we use. So, the Zetasizer technology I was talking about now, we assume that we're measuring a sphere, and we know what the theory tells us about how those particles scatter light. And then a lot of the challenge is how to backtrack from that theory into what our actual measurement tells us. But yeah, we do have a number of theory or theoretical scientists. So in fact, one of my colleagues, his previous job was as a theoretical scientist attached to CERN. So the Large Hadron Collider, so a different type of particles there, so subatomic particles, but yeah, a strong sort of theoretical background. So yeah, every flavour of STEM we have here at Malvern.
Fantastic. No, really good. Well, thank you ever so much, Alex, for sharing the facility with us this morning and for joining us today and jumping in advance as well. Do hang around in case there are any more questions in the chat, and then hopefully see you again soon.
Okay, cheers. Thank you very much.
Thank you very much.